So what we've been doing is talking about mixed, the mixed procedure, and how it works. What we've done is we've looked at the fact that it's fitting this model, this linear model that allows for random effects if you want random effects. You could have a marginal model, you could have a conditional model, but we're putting off talking about a conditional or transitional model until might not even be next week, and it might even be the week after. But in any case, this is the model we're talking about fitting. The beta represents the fixed effects. The BI represents the random effects in the model. The E represents the error term, and then there's an R matrix and a G matrix, which you have to make a decision about. And the R matrix describes the covariance structure that can be corresponded to a correlation structure. You remember there's a covariance structure and a correlation structure you can go from a covariance to a correlation structure or the other way around, and the R and the G represents the covariance structure for the R represents for the error term, and the G represents the covariance structure for the random effects term. And when you have a linear model, it turns out that once you specify or write the code in your program that tells the computer what the R and the G matrices are, then the correlation structure for the outcome is determined using this formula ZG prime plus R. And so that's the general formula for it. But typically when you run your program for your data using Proc Mixed, and you put in whatever your variables are, and you write the code for whatever the code is saying that's going to determine the R and G matrices, the computer is going to work using this formula ZG prime plus R, but you're not, because it's going to wind up giving you an output for what the estimates of the correlation structure is, given what you've given it, and it's going to come up with the estimates of the fixed effects, and if you have random effects, estimates of the random effects. And you're not really going to have to worry about working through this in practice, but this is what's being done. This is what, and again, I guess I realize that talking to some of you from time to time over the last few weeks is that, I don't know, the level of what we're talking about in this course is a little bit more difficult than the level in EPI 740, is that right? It's a little bit higher mathematically, it's a little bit more difficult because you're having to deal with well, some new methods, which you haven't quite gotten to in terms of GEE, but you're having to deal with matrices now, and you just having to get used to some new programs and a new issue, that's the correlated data issue. But if it's very important that you keep in mind, this is what I was talking to Zach about today when we met, that, I mean, the whole main, again, I've said this a few times, that the main reason for this course, if you think about it, again, is that when you do many epidemiologic studies, you wind up finding that you have repeated measures, you have correlated data, and that you have to do something about it, or you have to worry about whether you should do something about it, and you have to have some ways to do it. And that's what this whole course is trying to deal with, is trying to give you the background for what you have to understand to be able to do that, to give you the computer programs that you have to use to be able to do that, and to give you some experience through working through some homework examples and computer, particularly using the computer to do that with these programs, and then eventually the experience you're going to get from the projects to be able to feel comfortable that you can do this. But the idea is simple. You got correlations you're worried about. You're trying to deal with it somehow. You're trying to adjust your analysis to correct or adjust or take into account the correlations. It's almost like the correlations are like covariates or almost like confounders. You're trying to do something about it. And that's the purpose of the course. So keep bearing that in mind, even if you start getting stuck with some formula or some matrix formula or something. And again, please, it's hard to ask questions in this course. It was always hard to ask questions, I guess, in EPI 740. It's even harder in this course. Is that right? I'm not getting many questions from you. So you can always ask a question saying, I'm not sure what you just said. Could you say it again or something like that, I mean, that's okay too. But anyhow, that's the model we're dealing with. We talked about some various things about how it works and all that. We looked at the syntax for the model and, of course, for using Proc Mixed, and the key aspects of the syntax are the model statement, where you have to tell the computer what's in your model, and that statement actually tells the computer what the fixed effects you are in your model. And then you have random and repeated statements, the other two key things that you can use. You don't have to use them. And the random statement is the thing that tells the computer what your random effects are. And also in the process of doing that, it tells the computer what the G matrix should look like, in some sense, what the computer has to do to estimate the G matrix. And the repeated statement is basically telling you what the R matrix is. And you need to use that in order to consider any correlated data involving a marginal model. You have to have a repeated statement in there. In fact, if you don't put in, let's make sure we understand this. If you don't have a random statement when you're writing a code for using Proc Mixed, if you don't use a random statement, what does that mean about your model? What are you assuming about your model if you don't put a random statement in there? That it's definitely a marginal model, or it could be a conditional model, because you could have an earlier value of y. Again, we're not talking about it yet, but you could have an earlier value, but you're not having a random effects model. The G matrix is 0. There's no G matrix if you don't have any random statement. If you have a repeated statement, then you have an option for the repeated statement of telling the computer what the correlation structure is. In fact, you can even do that for the random statement. With the random statement, you can tell the computer what the correlation structure is if you have more than one random effect. And so you have, for both the random, for the G matrix and the R matrix, you can give it a correlation structure. Now, if you leave off the repeated statement when you're writing the code, what does that mean? What are you assuming about the R matrix? Are you assuming that there's no R matrix? What are you assuming? You're assuming that the R matrix is independent. That's what so even if you leave it off, you're assuming that you've got, if you leave it off, you're assuming what's called conditional independence. If you leave it off, you still are assuming an R matrix. If you leave off the random statement, there's no G matrix. The G matrix is 0. There's no random effects. I mean, just to make sure you got that. And then, of course, we were talking at the end of class, and I'll talk about this a little bit more as I start up here today, about contrast and estimate statements and how they work, and how you code them, and what the output looks like. We need to talk about that some more. And I will, at some point, as I do this somewhere over the course of the afternoon, I'm going to talk about contrast statements are statements that allow you to test hypotheses about various betas in your model, okay? Now, there are also ways to test hypotheses about the random effects, whether they're significant in your model. And I'm planning to talk about that today. I hope there's so many things I want to get to. I want to get to that. How do you test for random effects? And what do you mean when you're testing for random effects? What are you actually testing? What's the parameter that you're testing? How do you state the null hypothesis if it's a random effect? And how do you do it? And there's a number of different ways of doing that. So contrast and estimate statements. By the way, what was I was just thinking about something I was going to say, and then I forgot it. As I was, I also, I don't want the things I was going to say. We will have one of you folks are going to get up. Actually, you're going to be a team, maybe a team, and they're the three of them are. Monica, Michael, and Kate are going to talk about their project. So at least what they think is going to be their project, or what they hope is going to be their project, and they're going to describe it to you today. So there's going to always, as much as I can, there'll always be at least one group of you saying something about your project. And again, I'm still looking for volunteers for other weeks. I do have a group for next week, and maybe if I don't have so many things to keep talking about, to using up the time, I could have more than one group do it. But And if I don't let that happen, we're going to run out of time to have all the groups give a presentation before they give a presentation, before it's time to give the presentations at the end. By the way, remember that in the list of project groups that I've now got for everybody except a couple of people, those people who are taking the course for pass-fail, SU, they don't have to do a presentation at the end. And there are at least 3 groups in that fashion. So I got 12 groups that are going to give presentations, at least 12 groups that are going to give presentations, and we'll be able to have time to do that at the end to work that into the last couple of weeks of the class. So, okay, so we talked about this issue about what if you have missing data and how can you make sure the computer knows where the missing data is. Talked a little bit about that. Talked about the FEV example and the 2 issues with the FEV example, where one question was, the overriding question was you had these 5 weeks of FEV measurements on 40 kids, and you wanted to see if there was, over the 5 weeks, whether the average FEV score over the 5 weeks were different. That was one question. And the other question was trying to identify individual kids of these 40 subjects, which might have been more affected by the pollution episode than other kids. And we talked about that and spent a little bit of time going through how you do it. I talked about how you can deal with, you can use Proc Mixed to analyze missing data. If you do have missing data, there's no guarantee that the estimates of the regression coefficients or the standard errors are always going to be the same, even if you're using the what's so-called empirical option, which I also talked about. What's the empirical option? Just want to make sure I'm running through a bunch of, what do we mean by the empirical option when you're using Proc Mixed? What does that do? That's a way of adjusting what? What does it do? It's trying to take into account the fact that you may have specified the wrong correlation structure. And what it's doing is, it's not giving you a new correlation structure that adjusts the old correlation structure. It's actually adjusting the standard errors that you're getting in your output for the fact that maybe you used the wrong correlation structure and trying to do something to adjust the standard errors somehow. Exactly how that does that, we'll talk about it, but when I actually show you how it's done, I mean, I'll actually show you a formula down the road. When you see the formula, you're going to say sort of thank you, but no thanks, because it's a matrix formula, and the computer's got it built in there, and so do you really care what it looks like mathematically? But it's nice to know what it, and actually the formula for doing the adjustment, it's actually got a name. It's called a sandwich estimator. Sandwich estimator, which, you know, sounds like something you're going to, it's of the form, the reason why it's called the sandwich estimator is when you look at the matrix form, and this is about as far as I want to say until when I show you what it is for 1 second, it's a sandwich estimator because what's a sandwich? You got, if you're talking about a sandwich, you got 2 slices of bread, or some kind of, let's say 2 slices of bread, and you got something in the middle, whether you're a vegetarian or meat or something in the middle. So it's an estimate where the formula is such that on the, it's product of 3 matrices, and the 2 matrices on either end are the same, and the one in the middle is different. So the 2 on either end is like the bread. The one in the middle is the meat or the whatever's going in the middle of your sandwich. That's why it's called, who cares, right? But that's what it's called. That's what it's called. So anyhow, now one thing I forgot to talk about and wanted to talk about at the beginning of the class is it has to do with, now let's focus on the FEV data set. It has to do with when you're doing the testing hypotheses using contrast statements or however, or even if the computer might automatically give you a test, what the degrees of freedom are. The tests that you're getting when you're doing a test using Proc Mixed are either F tests or T tests. It's maximum likelihood, but it's not chi-square test because you're typically assuming normality, large sample normality of your data set because of the continuous outcome. And if you don't like the fact that it's continuous, it may not be normal, you could always transform the outcome. But now when we're dealing with the FEV data set, Remember, there were 40 subjects, there were 5 weeks. So the total number of observations, if there were no missing data, 40 times 5, 200 observations, okay? And if you wanted to do a chunk test for whether there's a significant overall effect of the weak variable. Now, if you remember, I don't have the model here, I have it somewhere else in these notes, but the model for that test, regardless of what the correlation structure you're using, had 4 dummy variables for the 5 weeks. Remember, 4 dummy variables for the 5 weeks, and had an intercept term, a beta 0, a beta 1, beta 2, beta 3, and beta 4. And you had an option, always have an option if you're using dummy variables for a categorical variable, how to define the referent group. What I showed you was the model expression when the referent group was week 5. The next homework assignment you have to do is working with the FEV data when you're going to assume that the referent group is week 1, and you're going to hopefully carry out how to do the same analysis, but when the referent group is week 1, so you get some practice with this. But in any case, there were a total of 200 observations, 40 kids, 5 observations per kid, and the model had a beta naught and 4 betas for corresponding to the 4 coefficients of the 4 dummy variables. So there were 5 fixed effects in the model, 5 betas in the model. Okay, so one way to come up with the degrees of freedom for the F test is to do get what's called the typical way one does in most linear regression models, whether it's correlated data or not, is you take the total number of observations and you subtract from that what? The total number of parameters in your model. 200 observations minus 5 parameters in the model is 195. So that's why you see the 195 up here. So that's a way the computer will give you a denominator degrees of freedom that corresponds to this so-called residual way of doing it. But it turns out Proc Mixed allows you to compute the denominator degrees of freedom other ways, and it's a little confusing to know which one to use. And so I'm going to give you some advice about it in terms of what I think you ought to use about what. But if you use it, the first bit of advice is that if you're using a marginal model, no random effects in the model, just a marginal model, okay, or it even could be a conditional model. Where you've got, but you don't have any random effects in the model, then my recommendation for what the denominator degree, how it should be done, is it should be this residual thing, where you actually, the total number of observations minus the number of parameters in the model, which in this case, in this example, would be 195. Now you notice that if you look at this table over here, where I've run for the FEV data, this is for the complete data set, and this is for the missing data set. For the missing data set, I dropped out 25 observations. So there weren't 200 observations, there was 175 observations, okay? But you notice that what I'm expressing here on this on screen here is I'm running the model. I'm running the same model, but I'm using different correlation structures, and the first 4 of them are all they're all different marginal model correlation structures. The first one assumes independence. There's no G matrix in the first 4 of them. The last one is AR1, and CS is compound symmetric or exchangeable, and UN is unstructured. And when I run each of those models, the degrees of freedom that I'm showing you here is 195, because that's what I generally recommend you use, because the only thing you're worried about estimating, the betas in the model. You don't have any random effects that you're trying to estimate, because there's no random effects in the model. It's a marginal model. Now, you could also argue, however, and some people do, argue that, well, okay, it's true, the model only has these 5 parameters, beta naught, beta 1, beta 2, beta 3, and beta 4. But it also has other parameters that you want to estimate. What are the other parameters? If you, for example, you're assuming independence. What other parameter do you want to estimate in addition to the betas? You want to estimate, you've got an error term, so there's a variance, there's a sigma square corresponding to the error term. So what about that? Do you do any adjustment for the fact that you're estimating the error term? Well, you sort of do. You take one less the number of that's one thing you do. That's why it's often, you often subtract one from getting when you're doing degrees of freedom. But what about compound symmetric or unstructured? Unstructured, how many parameters are you estimating with unstructured? Are you just estimating the betas? Well, you see, you're also trying to estimate those covariance in the unstructured correlation matrix. All these covariances are assumed to be different, and the variances might be different. It could be the same, but let's assume and so you've got a lot of parameters. Should you adjust the degrees of freedom when you're fitting a marginal model for the fact that not only are you estimating betas, but you're also estimating these other parameters? And my feeling is, since you're only estimating the betas, you shouldn't do it. If it's a marginal model, you should, although different people might say you ought to adjust for it. It turns out that, you see where I said, I've got this 195 and I got this, I guess it's a dagger. Dagger means danger, it's a dagger. Down at the bottom I say 195 is n minus p, n is 200 in this case, 5 is the number of parameters, and this is the residual, what's called the residual way. When you run a model, there's a code that you can actually put in. You could say DDFM, with denominator degrees of freedom, equals residual, and it's telling the computer to do this, to get 195 in this case. If you don't say DDFM equal to residual, if you don't actually write that, there is a default thing that the computer does, and it doesn't use residual. It does something called between within. I think I may have it on, it does something. See, it says DDF between within on the next slide. On the next slide, I've actually got different options for what you might write. And the key thing where in the code that you can tell the computer what you want the denominator degrees of freedom is DDFM. If you don't say DDFM when you're writing the models, that's where you write it, in the model statement. If you don't say DDFM, there's a default. If you're using a marginal model, the default isn't the residual. The default is something called between within. And you notice the between within, turns out that when I actually run this model, the default using between within, actually, if you go down, you notice down here, 1, 2, the third thing, you see it says DDFM equal between within. That's where I'm actually telling the computer the code, that's the residual I want to use. If I do that, the denominator degrees of freedom that I get in the output, I'm just showing you it, even though I'm not showing you the whole output, is 156, not 195. And that's what I actually get if I run this, or if I run it without saying what I'm using. I use the default, I'm doing between within. So, but you notice somewhere in here, is it somewhere in here? You see down here, 1, 2, 3, 4, down here it says DDFM equal residual. That's where I can tell the computer that's what I want you to do. Or I can tell it any one of these things. If I give it different things, I could get different denominator degrees of freedom could result in a slightly different or maybe a major difference in what the result of the statistical test is. Now, again, what I'm saying, if it's a marginal model, I strongly recommend that you just use the residual. Even though you can get, if you don't say DDFM equals residual, you're getting some other things being used. Now, where does the 156 come from? How did I get 100? You notice there's 156 down here. Now just look at the model that's being done down here. Down here. There's a complete data set. Sim means what? Another way of saying you're assuming independence. You're assuming the R matrix is independent, and in this case you only have, this refers to a 1 by 1 G matrix. If the G matrix is 1 by 1, what is how many random effects are you putting in the model? G matrix is 1 by 1, it's just one, you're putting in a single random intercept. Okay. So you don't have two random intercepts. You don't have to worry about the correlation between whether they're independent or not. So saying independence for that one by one isn't really saying much because you don't have to worry about it. But in any case, you notice when you have, this is the situation when you have an R matrix that's independent and you have a model that has a random effect and you got 156. How did you get that? How do you get 156? Well, again, 200, total number of observations. 5 is the number of parameters in the model. It gives you 195. What's the difference between 195 and 156? And the answer is 39. Where did that come from? How many subjects do you have in the study? How many clusters were there? 40, right? There were 40 kids. How do you get 39 from 40? You subtract 1. Why do you subtract 1? Well, typically, usually when you think you're estimating 40 things, usually you take off some degrees of freedom because when you know 39 of them, the 40th is already determined. That's why it's 39. So the reason why this is 156 here is because in this case, this model over here, where you're putting in a random intercept, in addition to having an R matrix, which is assuming to be independent, what are you estimating? Well, you're estimating these 5 betas, beta 0 through beta 4. What are you also estimating when you get the output? What do you also get from the output? You get these estimates of the 5 betas, and you also get estimates of what? You get estimates of the random effects. How many random effects are there going to be? There are 40 subjects. There are going to be 40 random effects. I mean, I even showed you that somewhere or other way back when we showed the results. I had it in another slide, but you wind up getting 40 random effects. So basically, and then 40 minus 1 is 39. So if you actually, so what you're doing is you're saying, well, look, I'm estimating 5 parameters, and I'm estimating 40 B's, which is really 39 because once I have 39, the 40th is determined. You have to assume that that's the way it works. And that, when you subtract 39 and 5 from 200, that's how you get the 156. Okay. So how do you get 117? Where'd that come from? What's the difference between this model and this model? You notice it says 2 by 2? What does that mean? It's under the column G. It means the G matrix has the dimensions, it's 2 by 2. It means how many random effects are in your model? 2, right? This was the model that I was pushing that you should use if you really want to answer the question, the secondary question about which kids were affected by the pollution alert. You had to add a second random effect that had the point that was 0 if you were in week 1 and 1s if you were in weeks 2, 3, 4, 5. That was a second random effect. That was a second column of the Z matrix that was put in there. Okay. Now, since there are 2 random effects, well, what are you going to subtract? You subtract. You got 200 observations in total. You subtract 5 for the fixed effects. You subtract 39 for the first random effect, and you subtract another 39 for the second random effect. That's how you get 117. And that's where these numbers come from. Okay. So if you're using, so the 156 and the 117 aren't what you're going to get from the residual degrees of freedom, from the DDFM equal residual. The residual would give you 195. So if you say use the residual when you're doing this, you're not going to get what makes sense. I mean, it makes sense to say 156 in this case because your model does have more than just the betas. It has these B's that you want to estimate. If you don't want to estimate, then maybe you could say it is 195, but why put the B's in there? Unless you wanted to consider estimates. So anyhow, that has to do with the denominator degrees of freedom. Now, as it turns out, as I sort of was saying, and this is where I don't want to overdo it here, but there are a whole bunch of choices. There's another option called the contain option. It's another option for choosing the degrees of freedom. So now you're saying, wait a second, this is driving me nuts. What do I use? Okay? And my recommendation, if it's a marginal model, don't worry about between, within, or contain. There's even another one called, where is it? I don't think I have it here. The saddest weight. Saddest weight. What's not? And then there's even another one, the Kenwood-Roger. I guess that's two people. I don't think it's Roger Kenwood. I think it's two, So people, statisticians like to have something to do, so they come up with different ways, maybe. So in any case, the contain option is something that generally works when you're doing a correlated data involving an ANOVA situation, an analysis of variance situation, an analysis of variance correlated data situation. Now, I'm going to talk about that very soon because that has to do with the homework assignment you had to turn in today. And the homework assignment even for yesterday has to do with that example, the shoulder flexion example, where you had 19 subjects, and each subject was observed on 3 days and 2 times of the day. And so you had sort of an analysis of variance type of situation because you had a factor called days, you had a factor called time, and you might even have the interaction of days with time. That's sort of an ANOVA situation. That's the kind of situation it makes sense to use the contain option. And, but in any case, so what I generally recommend, use residual if it's a marginal model, use a contain option if it's an analysis of variance situation, and maybe use the between within if you've got some random effects and it's not an ANOVA situation. That's how the 156 would be justified in that case where I had only one random effect. Do you follow what I'm saying? I mean, there's different ways to do it, and I have a whole page or two in the chapter on this thing, but it's really sort of a mess. I'm just giving you some guidelines on what to do. And that's, to me, that's the thing that usually works. Now, so let's go on a little bit, and I'm going to continue to go. We went through this. We went through this. This is where, for example, you notice that for this model, just to repeat, for this model, how many random effects are in this model? How many random effects are in this model on the top of the screen here? One random effect, right? I know you got your notes, so you're trying to find it in your notes, and I'm skimming around, so I don't know, But so I have to do something here. So in this model, there's one random effect. You're going to get 5 estimates for the 5 betas, and then you're going to get a bunch of estimates for the random effect. And since there are 40 subjects, you're going to get a list of 40 estimates for the intercepts for the 40 subjects. So that's why you're estimating not only these 5 things, but you're getting 40 other things. Okay? When you have this model that has 2 random effects, not only are you estimating the betas, there are 5 parameters here, but you're also estimating not only 40, you're estimating 40 intercepts and 40 random slopes in the model that correspond to the slope of the second random, the slope of the second random effect in the model. So there are 40 and there are 80, but it's 39, so it's 78, and that's how you get the 117. So, okay, so now let's get to where we were right at the end of class last time. This is what I was doing near the end of class last time. I'm just sort of trying to rehash some things that we did before, adding something about degrees of freedom, and now I want to talk about contrast and estimate statements. And I did a whole bunch of it, but I want to just rehash that or refresh you on that. So if you want to test a hypothesis about a fixed effect, I'm not right now talking about random effects, about a fixed effect in a linear model. Well, one way to do it is let the computer do it if it turns out the fixed effects are all in there as it's all in there, the fixed effect you're testing is in there in the model statement, directly in the model statement. So for example, to give you an example, the FEV data set. If the model had the variable, just like on this slide here, this is this slide. See this model? FEV equal to week /S. Okay. So what is this saying if week is in there as a class variable? What's in the model? 4 dummy variables for the 5 weeks, right? That's what's in the model. Okay. Plus an intercept, because you didn't say anything about leave out the intercept. So the model has 5 parameters. By writing this model statement, you're right. Now, you notice there's no repeated statement, there's no random statement. So what kind of a model is this? It's a marginal model. What's being assumed about the correlation structure? Independence. If I wanted to get a different correlation structure, what would I have to do with a marginal model? I'd have to write, I don't know if you follow me, but maybe I'm just going too fast off the top of my head here. If I wanted to run a marginal model that was not independence, I'd have to add to these statements another statement. What would it be? A repeated statement. And in the repeated statement is one of the options, /, I'd have to tell it whatever the correlation structure, covariance structure I wanted to use. If I wanted to use unstructured, I would say / type equal to UN for unstructured. Type equal to CS for compound symmetry. Okay, but I didn't do this here. Okay. Now, the thing is, in this particular model, in this particular set of code, and I said this last time, but I think it's important that I repeat it. This particular code actually gives you 2 different tests. Well, actually, technically it gives you 1 test, but because this other code is giving you an estimate, okay? What's automatically tested from this is what? From these statements, what's automatically tested? I mentioned it last time, but I want to see if you either remember or thought about it. What's automatically tested from these statements? You notice there's no contrast statement, but something is going to be automatically tested. And it has to do with the first statement I had up here. You do not need a contrast statement to test for an overall effect of a single variable, spelled incorrectly, as a fixed effect in the model statement. This includes class variables and their interactions as long as they're listed in the model statement. Tests are automatically output for each individual variable in the model. So, what can you test here? By saying that the model is, the week is a class variable and the model is FEV equal to week. What's automatically tested? Week, whether there's an overall effect of week. That's what's automatically output. Now, this is just the code, so it's not giving you the output. Okay. Now, it turns out you're also getting another bit of output from this, in addition to getting what the model looks like, and you also got another statement here, estimate week. Well, what's this doing? What's the estimate week statement doing? That's giving you an estimate. What did you say, Kate? You said that. Whether the week 1 is different from the other weeks. Now, how can you see that? Because you see it says, first of all, it says week. So we're talking about the week variable. And then it's got 5 numbers over here. Okay? And the first number, because it's week variable, and the week variable was coded for 1, 2, 3, 4, 5, okay, this is the first week, and these are the other 4 weeks. So what you're doing is you're comparing the first week to the average of the other 4 weeks, because the average of the other 4 weeks is the sum of the 4 means divided by 4, which is minus 0.25. You're subtracting that from week 1. Okay, so you're also getting an estimate of the difference between week 1 and the average of the other 4 weeks. Is that a random effect? Is that a random effect? Why do you know it's not a random effect? Well, there's no random statement in the model. There's no random effects being fit. This is just asking to get an estimate about some of the parameters. It turns out there were 5 beta parameters about some of the parameters in the model. That's what this is doing. Okay, so you're also getting that. Now, so let's look at model 1. Let's look at the output. Now, I'm going to skip a little bit here. I want to show you the output, so I'm going to skip to here. I've skipped a couple of slides here. And what number page is it? It's slide 36, in case you want to find it. But Here it is. Okay. Now, this is one. This is the first set of code. Okay. Now you see down at the bottom it says type 3 tests of fixed effects, and you see it says 495, 24.50. What's that? What's that? What's that giving you? That's the test for whether there's an overall significant difference between the 5 average FEV scores. Okay, it's 4 degrees of freedom in the numerator because 5 weeks, 4 dummy variables, 4 degrees of freedom for the weeks, and it's 195 if you're using your residual way of determining the denominator degrees of freedom. And so 24.50 is an F statistic for testing what's the null hypothesis. What's the null hypothesis being tested? That the 5 mean FEV scores over all 40 subjects are all equal. You've got average FEV, and you're saying what they average is that's what you're testing. Okay? And you automatically get that from this code, wherever it is, from this code, because you have week in there as a class statement, and you put week in there as the variable that you're putting in the model, and you're getting automatically that without having to worry about writing a contrast statement. You don't have to write a contrast statement. On the other hand, now let me find another code that I want to illustrate where you wouldn't get that. I'm going to try to find it. Let's go back to here. Look at this last code, and I'm going to have it blown up here. See number 4 over here? See number 4? Okay. Now I'm going to have it blown up slightly blown up here. Here's number 1. Here's code 1. And here's code 4. What's the difference between code 1 and code 4? You notice code 1 doesn't have a contrast statement, but code 4 does. You see it? Code 4 has contrast, and it says week, W11, W21, W31, W41. Okay. Why? What is this doing? What is this contrast statement doing? And what's different about this code than that code? What's different? Am I fitting the same model? Let me ask you that. Am I fitting the same model? Yeah, but am I doing it the same way? I'm doing it differently because the second model, or number 4, is using dummy variables to define 4 dummy variables for the 5 weeks. They're called W1, W2, W3, and W4. Those are the 4 variables. So I'm telling the computer I want you to run a model with those 4 variables in there. Okay? That's what I'm doing. Now, it turns out that if you want to test whether the coefficient of those 4 variables are all equal and equal to 0, you can't do it without putting a contrast statement in there. Because these 4 variables are listed separately. They're not one variable, like week. They're separate variables. So you have to write a statement that allows you to tell the computer that you want to test whether all 4 of them are equal, and this is the way you do it. W1 is 1, comma, W2 1, comma, W3 1, comma, W4 1, colon at the end. This set of statements does exactly the same thing as what this set of statements would do in this particular case where you've used dummy variables to define the weak variable. So you can do it either way. Now what are you going to do? You do whatever you want. If you want to use class variable to do it that way. If you want to use dummy variables to do it that way, do it that way. It's up to you. But there are 2 ways to do the same thing. Okay? That's, I don't know. So 1 and 4 give the same overall F test. They both test whether the overall 5 means are equal or whether the 4 betas that correspond to these 4 new variables that you've defined are all equal to 0. In fact, if all 4 betas are equal to 0, that's equivalent to saying that all 5 means are equal to 0 also. So that's what you can. There are 2 ways you can do a test, and if you don't have the variable defined as a class variable, you're going to have to actually write a contrast statement. That's what this does. So let's look at a couple of other things here. Now, and this is what I did last time. Let's see here. Okay, let's look at, again, let's look at code 1 and code 2. I showed you this last time. And let's look at the estimate statements for both of them. The estimate statement here and the estimate statement here. Are they the same? And the answer is no, right? This estimate statement is different than this one. What's the difference? Well, first of all, this was based on a code where you used a class variable to define week, and this is based on a code where you use dummy variables to define week. So if you want to estimate something, you have to specify the code differently. Okay. Now this says, as we saw, 1 minus 0.25 4 times here. This is comparing 1 versus the average of the other 4. The means, because there's 4 weeks, the means for the 4 weeks. Those are the weeks represent the parameters of interest. Okay. Now what about this? What's being done here? What's being done here? And I showed you this last time, so maybe I'm overdoing it here. Am I overdoing it? I'm not sure, because in any case, see, W1 is a different parameter, is a parameter for a variable that you defined as a dummy variable being takes on the value 1 of week 1, 0 otherwise. Okay. And W2 is another variable that corresponds to a beta parameter. So this is a beta 1, this is a beta 2, this is a beta 3, and this is a beta 4. And you notice there, as I mentioned last time, there are 3 minus 0.25s here, not 4 minus 0.25 here. 4 of these, there's only 3 here. So what this is saying here is, this is looking at the estimate statement, or what's called the contrast, comparing beta 1 with the average of beta 2, beta 3, and beta 4. There's no beta 5 in here, right? This is comparing beta 1 with the average of beta 2, beta 3, and beta 4. The average, it's not really the average. The sum of those 3 divided by 4 is what it is. It's minus 0.25 times W2, minus 0.25. So why does this work? Why is this the same thing as this? Because if you do a little algebra with this thing, well, if you think about it, beta 1 is defined by the first variable, 1 of week 1, 0 otherwise. So beta 1 is really the difference between week 1 and week 5, because week 5 is the reference group. And beta 2 is week 2 minus week 5. And beta 3 is week 3. So if you plug all these things in and you work through the algebra, you wind up finding out that beta 1 minus the sum of the other 3 divided by 4 is actually equal to U1 minus the average of the other 4 over 4. So doing this is equivalent to doing this. Okay? So which one do you want to do? Do either one. 2 ways to do the same thing. Okay, you decide. Okay, what do you get? What would you get from this? Well, let's see what you get. Let's see what you get. Okay, now in order to see what you get, let's just look at this. Look at this. This slide. Okay, now on this slide, or let's see. Okay, on this slide. Okay, contrast and following the 5 weeks. I don't know if you remember, but the overall average. The overall average at day 1 was 9.8. The overall average at days 2, 3, 4, and 5 are these numbers: 6.8, 7.0, 6.95. So if you wanted to ask what's the difference between the average at week 1 versus the average of the other 4 weeks, you get 2.8637. That's what the algebra does. If you just do these 9.81 minus this thing is 2.8637. Okay. That's what the estimate statement is trying to estimate, the difference between week 1 and the average of the other 4 weeks. And either one of these two statements is doing the same thing. Okay, now let's see what it gets. Okay, look at the bottom of this screen where it's got 1 and a 1 here. I am skipping around, so. But look at the bottom of this screen. You see this number down at the bottom of the screen? What number is that? If if you can see it. 2.8637. That's the number I just showed you, 2.8637. Now you notice this is the result of using the first code. The first code had a 1 minus 0.25, minus 4 minus 0.25s. And that's what you got for the estimate. So if you want to estimate this, not only do you get the estimate, but you get its standard error, and you can also get a confidence interval if you know the estimate and the standard error. And I think you can get a confidence interval by adding another statement to the code, but I didn't do that. But in any case, that's the estimate, 2.8637. Now just let me show you what I'm saying is if you use this code, you're going to get 2.8637. I'm also saying if you use this code, you're going to get 2.8637. Because you're doing the same thing, just using dummy variables instead. Let's see that. Where is it? Here it is. This is the second code where I've used the dummy variables. See at the bottom? What do you see? 2.8637. So you're getting exactly the same answer because you're doing it using dummy variables, so you're doing the same thing. It's just, so there are two ways you can do this. And you have to decide whichever way you want to do it, as long as you got to be a little careful to know which way do you want to do it. It depends on whether you want to use class variables or not. Do you like to use class variables? Well, maybe you say it gets you confused. So maybe dummy variables, you can see what you're doing. Maybe not. So anyhow, this statement, as for the code for the statements 1, will give you the same thing. Now let me show you one last code. Look at this code. Look at this code. This is for 3. Look at the code over here, and look where it says, look at this. Now wait a second. Okay. Okay. Look at this code here. First code. I already showed you this. 1, 1, 1, 1. What about this? What's this doing? What tests are being done? How many tests are being done from this? How many? It's only one test because there's only one contrast statement. Are you getting a test for the overall effect of the difference between the 5 weeks from this code? And the answer is no. You'd have to use this set of statements that I used for the set of code for 4 in order to do this. W11, comma. But so what is this testing? What is this testing? This is a test because it says contrast. What's it testing? It says contrast weak. But weak is not in there as a class variable. So it says weak, W11, W2 minus. So what's being tested? What is being tested? What's being, what do you, if I had written estimate instead of test, what would be estimated? If I had written estimate weak, W11, W2 minus 0.25, what would I be estimating? 2.8637. I'd be estimating beta 1 minus beta 2 plus beta 3 plus beta 4 over 4. Now, so this is testing whether beta 1 minus beta 2 plus beta 3 plus beta 4 over 4 is significant or not. It's testing whether this 2.8637 is significant or not. 2.8637. And you notice that it's got an F value of 97.79. See that? And that's highly significant. Okay. Now, let me just show you something. Okay. Let's go back to, back to this previous thing. Back to code 2. See at the bottom where it's got 2.8637? And you see it's got 9.89? And you see underneath, above it, it's got a t value? Okay. To get an f from a t, what do you have to do? Okay, so if you square 9.89, you get, I guess, that's 97.79. And there it is. Okay. So it turns out that if you want to test for the significance of that contrast, not just get the estimate of it, but test for it, you need a contrast statement. If you want to just get the estimate, you need an estimate statement. So anyhow, the main thing is, okay, contrast and estimate statements are the things you have to use if you want to test hypotheses or get estimates if you're doing linear models. They're also what you have to do for nonlinear models, but linear models for when you're dealing with linear models with marginal, there's no random effects. Now, that's not what you have to do for random effects. So now I'm watching the clock here. Okay, now, what we've done up to this point, now I'm ready to shift gears here a little bit. I got a million things to talk about, but we only have 10 hours to do it today. 3 hours, 2.5 hours. Okay, so what we've done up to this point with the FEV example, the FEV example was an example that illustrated the use of random effects in the sense that when you wanted to say something about individual subjects, you had to use a model that had random effects. Otherwise, you couldn't say something about individual subsets without using subjects, without using a random effect model. Well, that's not the only reason why you might want to use random effects. Because, again, one of the issues that you're all going to have for your project is to what extent, for your project, do you want to use random effects in your project? Okay. So one reason for using random effects is you want to say something about the individuals in your clusters, the clusters. Another reason is you don't necessarily want to say anything about the individuals in your clusters, but you want to use a correlation structure that's more complicated than the correlation structures that your program gives you. That's what this says. You want to use a correlation structure not available as a choice in the computer package you are using, as for, as I say, a repeated measures ANOVA approach. And that's what the shoulder flexion example is. Okay? So I want to illustrate that. And that's what you had for homework, the last two homeworks. Okay? I'm just going to start talking about that. Okay? So here's the shoulder flexion example. Right? 19 subjects, and each subject's observed on 3 days and 2 times each of the day. You've done this enough. You know this data set. So there are, in a way, 2 main variables of interest, day and time. The purpose of this study, as I think I remember saying, was to see if over a given week, whether people's posture changed from one day to the next or one time of day to the next. You might think that later in the week, they're going to start being slumped over their desk or something. So maybe their posture's not as good. Or later in the day, it's not as good. Something like that, of the same day. So that was the goal. The goal was not to see whether your posture on a given day is going to cause muscular skeletal effects. That was a later question. But this question was whether posture is different from one day to the next, from one time of day to the next. That was the goal. Okay. So the 2 variables of main interest were day and time. Is there an effective day? Does it matter which day you're talking about? Does the posture differ from one day to the next? Does the posture differ whether it's AM or PM? Or does the posture differ in an interaction way? Is the day times time, if it's Wednesday morning, does that differ from Friday afternoon or something like that? That's an interaction question. So the main question, is there an effective day, is there an effective time, or is there an interaction between day and time? That's the main question. That's an analysis of variance question. But now there's another issue. Another issue is that you have correlated data, or you're worried about correlated data because you've got each of the 19 subjects been measured several times. So you assume that the measurements on each subject are correlated because it's the same subject. Okay, so you're worried about adjusting for correlations. Okay, so that's another factor that you want to bring into the problem. So there's day, time, and there's subjects. And if you could look at it and say, well, look, I know I'm mainly interested in day and time, and whether there's a main effect of day and time and interaction, but I also might want to say, I've got another factor, subject. Is there an effect of subjects? Is there an interaction of subjects with day? Is there an interaction of subjects with time? Is there an interaction with subjects and day and time, or something like that. These are all the questions. So in a way, it's really a three-factor problem. Is there an effective day, time, or the interaction is the main thing, but it's a two-factor. Sometimes it's called it's a crossover design. Why is it a crossover design? Why does the word crossover make sense here? Because what are the treatments? Day and time, Andrew.
Because the exposure differs over time.
Well, each subject got all the different treatments. I mean, in a way, it's some combination of day and time. Each subject got all combinations.
The treatment is like day, time.
Treatment is day-time combination. So each subject got all 6 combinations you could possibly get. So that's why it's crossover. Okay? And what you're worried about is the fact that it's same subject got these different things. You're worried about correlation. Okay? Okay, so now how do you do this? Well, there's a number of ways to look at it, but one way is just to say this is a correlated data problem. So there's a number of ways I could approach it. One way is to say, well, I got 3 days, I got 2 times, and I'm mainly interested in in these 2 effects and maybe whether there's an interaction. And I can look at the data, and that's one of the things you asked to do for the homework assignment, I think today, or maybe even last week, I'm not sure, to see whether the data looked like there was a main effective day or time or interaction. But, and now, given what you see here, the reason why I wrote it's a marginal model is why? Why is it a marginal model? Why is this a marginal model? The way it's written. There's no random, you don't see any random effects in there, right? So it's a marginal model. Now that doesn't mean you can't use a correlation structure that's compound symmetric or unstructured or whatever it is. You have 6 observations per subject. So you could use whatever correlation structure you want with that marginal model. You don't have to assume independence. You can fit a marginal model with whatever correlation structure you decide and be taking into account correlation. So that's one model you could choose. And here's another model. What's this model? Model B. What's model B? Well, model B is not a marginal model because it's got this thing, S sub I. Okay? S sub I stands for random effect for subjects. Okay? So I've added essentially a random intercept. I mean, I've called it S sub I and not BI0, but it's a random intercept. Okay? So this is a second model I could use that's not necessarily the same as this one. Well, when would these 2 models, and this is one of the questions you had for homework, when would these 2 models really give you the same answer? When would they give you the same answer? If you fit model A and you fit model B, when would you expect them to give you the same answer? That was the homework question. Zach went over it in the lab. When would they give you the same answer? Well, if it turns out there's no random effect, right? So this is a marginal model. You'd have to specify an R matrix. Suppose you specify the R matrix to be compound symmetric for this model, okay? Okay, since there's no G matrix, what's the covariance structure? What's the correlation structure? It's compound symmetric, right? Now, what if it turns out for this model, which has only one random effect, so the G matrix is what? It's just a scalar. It's just a sigma naught square, the variance of this random effect. And if I want to assume that the error, other than this random effect, what's left over, the error term is independent, sigma square I. If this is a random intercept, and this is sigma square I, and I combine this G matrix with this R matrix in the formula ZG, Z prime plus R, what am I going to wind up getting for my correlation structure, my covariance structure? Compound symmetric. So I can get compound symmetric 2 ways. One is no random effect, R is compound symmetric, or I could run this model with a random intercept and assume that the R matrix is independent. If I run either of those 2 models, I'm going to get exactly the same answer. Exactly. Because they're 2 giving me the same thing, except that I'm going to get the same answer for the fixed effects. For the random effects, I'm not going to get an answer from model A because I'm not putting in any random effects. But I will get random effects for model B if I wanted it. But if I don't care about it, which I didn't really care about it, I wasn't really interested in identifying individual subjects of the 19 that were affected posture. Maybe I was, but if I wasn't, it doesn't really matter. Now, here's model C. Then I'm going to talk about it and then take a break. Here's model C. I know it's break time, but here's model C. Now look at model C. What's different about model C? Now, this is a little different slide. It's almost the same as the previous slide that you have, but it's a little different because I added something to it. But now, look at this slide. You've got model C. Is that the same thing as model B? No, why not? Because what have I added? I've added S times D, 2S times D1, S times D2, and an S times T. I've added these three things. What are they? Are they fixed effects or random effects? Why are they random effects? Well, one part of each one of these things is a fixed effect, D1, D2, and T. But any product of two things, one part of which is a random effect, means that the product's a random effect. So I've added three random effects to this model. Okay? So what am I effectively saying here by this model? What am I doing with this model that I'm not doing in these models? Well, what I'm doing here, now there's a technical issue here, but what I'm basically doing here is I'm saying, well, look, I'm now thinking of subjects as another factor, in addition to days and time. And I'm saying, well, maybe there's an effect of subjects, or the random effect of subjects, but maybe there's an interaction of subjects with day, maybe there's an interaction of subjects with time. Maybe there's even an interaction with subjects with day times time, but I actually can't do that because to get that interaction, I'd have to have repeated measures I'd have to have more than one observation per person, which I don't have, in order to get an estimate of the three-way interaction between subjects, day, and time. So model C is equivalent to a three-way repeated measures ANOVA model because it's considering the fact that you have three factors. And it allows for the possibility of interaction of subjects within days and subjects with time. If the latter interactions are not significant, maybe you could reduce it to model A and B. But this is a more general model that you might want to consider that allows the fact that maybe the subjects are interacting with days and time. If you don't consider this model, you'll never know whether there is this kind of interaction. You have to decide that. Okay? Now, this is where I will stop, but technically what I've written over here is not right. What I've written here that was in your original notes is not the correct way to write this model. It has to be written differently, and that's on the next slide, which I'm going to talk about after the break. So it's 10 of, we start at 5 after 4. So after the break, I'm going to talk about this a little bit. Then I think I may talk a little bit more and then eventually have you guys do it before we quit, before the end of the day. I want to make sure you guys, but I have a bunch of other things a bunch more, okay? So 5 after 4, is that enough of a break? Are you weary? You are. You feel like you're being punched around a little bit? Yeah, sorry. I'm not trying to do it, but this stuff is punchy. Okay? I don't know. But 5 after 4, okay? Every week you have to sort of ask yourself, how much more of this am I understanding? I don't know. I'm not sure what to say, okay, let's go to the pause. So the main thing I was saying is that for the shoulder flexion example, you have options how to do the analysis. You could fit a marginal model and decide what correlation structure you want to use, and just pick some and see what you get. You could use a random effects model and pick some other correlation structures in addition to the random effects. If you pick the correlation structure to be independence, you're getting the same thing as compound symmetric here. Or you could decide to use a model like this, which allows you to consider a correlation structure that's more complicated that allows for not just random intercept, but random effects of subjects with days, subjects with time, subjects with, well, basically subjects with days and subjects with time. That's what this is allowing for. Okay, so if you try this, well, it's something, you know, one thing you could do is you could say, well, maybe this, since this is a more general correlation structure, maybe I'll start with this, see what I get. Maybe I can simplify things and not have to use this and get a simpler model. So, but I'm allowing myself to see something that's more complicated, or maybe not. So you got choices like this. And I'm not going to tell you what to do for your project. You're going to have to make, for your project, you're going to have to make some choices as you go along to try to answer your questions. And we'll have lots of questions and lots to choose from. So, okay, so now what I said, technically this isn't correct, because what I'm saying is correct is what I wrote down here at the bottom. Okay, what's the difference between here and here? Well, I mean, just looking at the two formulas. I mean, this thing adds, in addition to, you see it's got an SI1, D1, SI2, D2. They're there, okay? But it's got this thing that wasn't there. This thing wasn't in there. I mean, there was an SI3T, but I've now put a D3 in here. And this has got two different SI product terms, one involving time 1 variable and one involving time 2 variable. Time 1 is the variable time 1 is 1 if it's time 1, 1 if it's AM, 0 otherwise. Time 2 is 1 if it's PM, 0 is otherwise. Now, you don't want to put a variable like, you don't want to put T1 and T2 in the model here, because if you do, you're putting in collinearity in the model. You're putting two variables. Once you know one, you know the other. If you know somebody's at time 1, you know it's not time 2. So you can say which one it is, whether they're time 1 or not. So you don't want to have 3 Ds over here, and you don't want to have 2 T's over here, because you're putting into the fixed effects models is going to cause collinearity, and it's not going to run. Okay? When you're dealing with random effects, it's a different story. And the reason is that, as I say here, there are, just like if you just had the model with just if you just considered the random intercept, you're going to get 19 estimates of the random intercept for each of the 19 subjects. And what you're going to get for this thing is you're going to get 19 estimates of the effect of day for each of the 19 subjects. And you're going to get 19 estimates for the effect of this is day 1, this is day 2, and this is day 3. You're going to get 19 different estimates for day 1, day 2, and day 3. And if you don't put in this thing, it's wrong. Okay, now it turns out the code, when you're running the model, this is what the model looks like, but this is not the code for the model. This is just the model, okay? And you need this model because now I say more, if you don't use this code, this is not a code. If you don't think about that this is your model, and you're trying to get the computer, which computer can do without your actually computing this matrix, but if you actually try to compute this matrix, which was your homework question for this week, it was listed as extra credit. Extra credit, what does that mean in this course when you're not getting any credit for anything, right? So it's just an extra, more difficult question, you might say. And I have a feeling most of you didn't do it. Am I right about that? I have a feeling, because it's extra credit, and extra, it's an extra thing. But if you actually didn't write the model, if you wrote the model the other way, and you computed this formula using the model with this way, if you use the model this way, and you think about what the Z matrix will look like, look at this. For the model that I've written here, this is the Z matrix that corresponds to this model, the model that I've written down below, that's on this page, down below. This is the corresponding Z matrix in the ZG, Z prime plus R. But if I actually wrote, and this is heavier than I want to spend a lot of time on here, but if I actually considered the Z matrix that corresponded to this way of writing the model, and not this way of writing the model, I would actually leave off 2 columns from this matrix, 2 columns. I'd still have 6 rows. Could anybody tell me which columns I would leave off? I'd actually leave off the 4th column, and I'd leave off the 6th column. That would be the Z matrix that would correspond to that thing. And if I actually try to go ZG, Z prime plus R with the Z matrix that cut those columns, I wouldn't get the right correlation structure. And if I try to estimate it, I wouldn't get the right answers. So, and in fact, corresponding to this Z, the G matrix that you're dealing with is making you notice it's a 6 by 6 matrix, and you notice that up here you see sigma square S. What's that stand for? What's sigma square S? You've got a random intercept, and this is the variance covariance matrix of the random factors. So what is this? This is the variance of the random intercept. That's what sigma S squared is. What are these 3 things? This is the variance of the interaction between subjects by days. And there's an assumption being made here that they're all equal, which you might not want to make, but that's what, if you do this, you're making that assumption. Okay? And this is an assumption, this is saying this is the variance of the interaction of subjects with time. Okay? And that's the appropriate G matrix. And if you want to actually multiply Z, I mean, none of you really want to do it unless you really, some of you really want to get the handle of matrices. So if you do, you might want to do this for some homework assignment on a Sunday night at 3 in the morning or something that you have nothing better to do. But some of you like that, So, but anyhow, is that Jake? No, that's not Jake. You don't want to do that. I'm just flipping. Not picking anybody out in particular, but I picked you out just for some silly reason. Anyhow, now there's what it comes down to is there's another way you can write the model actually as an ANOVA model that you might have learned when you took the course from who was it? The course Bob Lyles. The way of writing an ANOVA model, where you say if you talk about the kth the ith subject and the jth day and the kth time on the ith subject, you're writing a model as effects. This is the ANOVA version of this model. But there are 2 ways of saying the same thing. So, but the reason why I'm saying this is that there's an alternative way you can actually do this analysis without using Proc Mixed. There's an alternative way using an ANOVA model. In fact, there's a program called, it's not Proc Reg, it's Proc GLM. Did you use GLM in Bob Lyle's course? I don't know if you did. How many said yes? So there's 3 of you, So I guess that means you did. The rest of you don't remember, or didn't want to remember. Okay? But anyhow, there's a way you can actually do this whole analysis using GLM by considering how, when you think about ANOVA, analysis of variance, I don't know if you remember about this. Analysis of variance is a way where you say, look, I've got an outcome variable, and that contributes a certain total number of sums, a total sum of squares. And what I'm going to do is I'm going to partition the sum of squares according to the effects of various factors. So according to days, according to time, according to the interaction. And then I'm going to have some residual terms, some error terms, according to days, times, and interaction. And that's another way to do that, and that's what the GLM program does. And what it basically does is you've got a total variation, and you separate variation between subjects and the variation within subjects. And when you're using this particular data for the shoulder flexion data, you notice that I have variation between subjects, and then I have variation, and you notice I have everything coming out of this box. Nothing, once I've got to this box, I don't have anything coming out of this box once I've got there. Everything's coming out of this box. Why? Because of this crossover trial. All the variation is coming from the fact that I've got, for each subject, I've got several observations on that subject over day and time. So all the variation, once I have a subject, is coming out of variation within the subject, according to what happened day, time. So that's the way the partitioning is done. And it turns out if you partition it, you can come up with an analysis of variance table that looks like this. That's what it would look like if you use GLM and you ask GLM to give you the ANOVA table. Now, what is this? If you didn't know exactly what GLM did, but you saw this ANOVA table, how would you use this ANOVA table? This is not mixed. How would you use this ANOVA table to decide whether there's an effective day, whether there's an effective time, whether there's an interaction of day with time? What would you do? Well, you'd look at this information and you'd say, okay, well, maybe the first thing I'll do is do what? What would the first thing you do? Or look at the interaction, right? Now, if I look at the interaction, is there significant interaction? No, because I get an F statistic, p-value is 0.50, okay? And what I get is a F statistic based on, you see this 0.79? Where does the 79 come from? You take this 14.63 and divide it by 18.43, and that's how you get 0.79. Now, these two numbers are two what are called mean square estimates. You remember something about mean square? You divide two mean square and you get an F? I don't know if you remember that from Bob Lyle's course. So these are two mean square estimates, and these are two other mean square estimates. You get, now this is the 18.43 is the mean square estimate that corresponds to day times time. And this is the mean square estimate. This is the mean for the error term for day times time. And this is for day times time on its own. Now, why that works exactly has to do with the way it works partitioning out these sums of squares. But if you look at this, and you look at this information, let's for now not worry about the fact that maybe it wouldn't be correct to just do these three tests by themselves, because maybe since it's what would you think that you'd have to do that would be different? In other words, one thing I could do is I could just look at these three tests, and they were all non-significant, right? They're all non-significant. One conclusion I might make is what? I mean, what was the goal of the study? Does shoulder flexion posture, does it differ by day and time? And what's my answer? No, 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 right? No, 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 right? Because this is no, 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 right? How could you criticize that if you were thinking of modeling? What you might want to do is you might want to say, well, look, I want to first answer the question about interaction. And if there's no interaction, I'm going to run the model again, and I'm going to partition it differently only using days and time. And then I'm going to test for days and time without an interaction term. So I could do it that way. That might be better, unless I can assume more or less these are independent. And it's questionable whether I can. So you might want to really drop the interaction term. But this suggests, I'm just giving you this suggests that there's no effect of shoulder flexion on the effect from day or time or its interaction on shoulder flexion. That's what you see here. You can see that. Okay. This is from not using Proc Mixed. Okay. Now, here's what you would do if you were using Proc Mixed. Okay, this is how you would do this using Proc Mixed. Okay. First of all, here's the code. Okay. Now, I've done a bunch of things in this code that I hadn't done before. I've got Proc Mixed, data equal to SF, stands for shoulder flexion. I've added something called Cove test. Okay. By adding this, I'm getting this information that I wouldn't have gotten if I didn't add this, particularly what's here and this other bit of information. The Cove test is giving me, if I didn't put Cove test, I might get the ratio and the standard error, but I might not get the Z and the p-value. So this is something extra. But look where it says class, subject, day, time, SF, day times time slash S. What's that doing? What's the model? What are the fixed effects in the model? There are two dummy variables for day. Day has two categories, three categories, so two dummy variables for day, and I've got it as a class variable. One dummy variable for time, and two product terms, day times time. That's the fixed effects part of the model, right? That's not that hard, okay? And then I put random intercept day times subject equal to SUB SJ. What am I saying here? What model am I using? Well, first of all, I'm saying in addition to fixed effects, there are random effects, okay? What are the random effects? One random effect, when you say random intercept, what are you talking about? Talking about just for subjects, right? Just saying subjects are different. It's like an SI term in that original, it's like this SI term, okay? What about these other ones? When I say random intercept day, what am I doing? Well, it's like intercept would be subjects. Day would be day time subjects, intercept of day with subjects, and time would be the intersection, the product of day with time, or the interaction of day with subjects with time. Okay, so that's what this is doing, and basically what I'm doing is that model. This is the code for fitting this model. That's what I do, and you know it's not that bad because it allows you to say, look, I want to have. And what I didn't put in was, you notice I have day time, day star time, but you notice I didn't have intercept day time and I didn't have a day star time. I didn't put that in. Why didn't I put that in? I already sort of gave you the reason, but I don't know if you remember it because you forget things easy in this class. Day time, why isn't that in there in the random effect? Andrew. You don't have multiple observations on each subject at a certain day-time combination. You'd have to have repeated measures on a certain day and time. You don't have any of that. You only have one observation per subject at a certain day and a certain time. If you had repeated measures, then you could estimate, but basically what you're doing, if you want to estimate error, what you're assuming is the error is that interaction of day with time with subjects. That's the only way you can get error. That's sort of what's happening. So you can't put that in. If you did, you'd get some kind of error message or some kind of, the model wouldn't give you any, you have a lot of zeros in the output and so on. Okay, so now look at all this and look down here at the bottom, not at the middle. Look at the bottom. Okay, what do you see at the bottom? You see these numbers? Have you seen them before? Yeah, same numbers, 1.78.02 and 0.79. Right? So you can use Proc Mixed to get this. That's what you do. Okay? Now, what's the stuff in the middle doing? What's the stuff in the middle doing? Well, it's giving you estimates of information that has to do with the G matrix. The G matrix. Actually, it also gives you information about the R matrix. Because the R matrix that you're assuming here, you notice there's no repeated statement. So what's the R matrix? Sigma square I, right? So you see where it says residual over here, and you see 18.4279? What's that the estimate of? You know, the R matrix is sigma square I, so what's 18.4271? It's the estimate of that sigma square in the sigma square I matrix. You getting that? Okay. So what's the 119.1725? What's that? Well, that's the estimate of the variance corresponding to the random intercept. This is the estimate of the variance corresponding to the intersection of day with subjects, and you're only getting one estimate because you're assuming that they're the same. Remember I had these three S squared, SD, three of them were the same, so I'm assuming only getting one of these, and this is the variance estimate for for time subjects. Okay. Now, now notice that Okay, so that's what you're getting here. Now notice there's a bunch of other information. It's got things called ratio. I'm not sure what that is exactly, but you have to divide something. 119 by 18, I guess, is 6. And 17 by 18 is point. That's what it is. You're dividing everything by this residual. For whatever that means, I'm not sure. But notice where it's got a z and a p-value down here at the end. Okay. You notice that the p-value for residual is small, as small as you can get to 4 decimals. But look at the p-value for the intersection, the time variable. What's that saying? What is it testing? What do you think this is testing? This is a way you can do a test for a random effect. What's it testing? Whether there's a significant random effect of time. And what would your answer be? No, right? And if you're assuming all these things are independent, you would say these other two are significant. So it looks like there's a significant effect. It looks like maybe you could drop the time random effect from the model, but maybe you have to keep the day and the intercept random effects in the model. But of course, you can drop the time variable and just go backwards and see whether, once you drop the time variable, maybe the day's not, significant, and you can still wind up having a random intercept. Maybe you can drop them all, okay? But this is one way to test for random effects. It's one of 3 ways to do it. And the unfortunate thing about it is that it's not the best way, but it's the easiest way. Most people don't do this, because if you do this and you don't do it any of the other ways, you might get the wrong conclusion. Because people who have spent some time talking about how do you test for random effects have found that this way, this is like, basically what you're doing is, this is like, you see the Z? You remember when you were doing logistic regression and you were fitting a logistic regression model and you did a Z test? What did you call it? The Wald test. This is like a Wald statistic for testing for the significance of random effects. And this is a way you could use this Wald statistic to do it. Okay, but and I'm not giving you the whole thing, because you might want to say drop time, redo the model, leave out. Well, drop time would mean what? What would if this thing was not significant? How would I consider refitting the model? What would I drop? I would drop the random effect for time, but I wouldn't drop day times time. I don't have any, because maybe I still want to keep that in there, but but these might change now. So I drop time, and I only have intercept and day, and then I'd look at this information. If I assume this was okay, a way to do it, this is how I would test for random effects. So you got the idea? I mean, this is the simplest way to test for random effects, but it's not the best way. And I need to talk about the best way. Okay. Do I have time to do that? Well, let's talk about it. Let's see what I do. Now, before I do that, however, there's always something before, okay? Now, look at this, the first model. The first model listed on this screen. And look at what I've written here. Proc Mixed, class, model, random. You see what's written here? This in red and this in green, okay? What's written under number 1 is exactly the same information as this. I just wrote it again. I didn't write Cove test. I left that out because I could have put Cove test in there. But if I run this, I'm going to get these results for the test statistics. That's what I'm going to get. But I'm not going to get this because Cove test gives me more information. I'm going to get part of this, but not all of this. Okay. Now, here's what I want to show you is, in addition, I'm still looking at 1. I'm not looking at 2 or 3. I'm looking at 1. Equivalent alternative code. Look at what I've written over here. What does that say? What am I saying here? I'm saying this is an equivalent. What I'm saying here, instead of writing this in green, I could have replaced it with this. And I'll get exactly the same thing. And one way you can see that is do it yourself. Now, I've got this thing on the computer. I've done it myself, So if I do this now, why do you think this works? Because look at this. See, intercept day time. When you're doing that, subject equals subject, what are you essentially saying? Intercept is subjects, day is subjects by day, and time is subjects by time, right? Isn't that what you're doing? So why don't you, as an alternative way of telling the computer to do it, just write subjects, subjects by day, subjects by time. Just do that directly. And once you do that, you don't have to say subject equals SUBJ, because you're using a random statement, but you're defining it very directly in terms of what the random effects are, the random effect of subject. You're not actually forcing it to be this times that. You're actually putting the variables in. And if you run this, you're going to get exactly the same result as running this with the other random statement. So there's two ways to do it. You know, as you can see throughout this whole day, there's a lot of different ways to do it. So which way do you want to do it? Well, it depends upon what you're dealing with. If the problem gets more complex, as it does for the next homework assignment, then you might want to do it this way, depending on how complex fixed and random effects you have. Look at the second thing. Look at the second thing. Now, this is just the simpler model. This is the first model A. This is model B. There's only a random intercept here. See that? Now, you see what I've written over here? Random subject / SG. Can you see that this is the same as that? Because instead of saying random intercept subject, I'm just putting in random subject. So these two are equivalent. Okay? Now, look at the third thing I've done. The third thing is, now you notice that neither of these first two have a repeated statement. But what's the R matrix for the first two? It's sigma square I, right? It's independent for the first two. I don't have a repeated statement, but there is an R matrix. It's always an R matrix. You with me on this? I'm not sure. Okay. Now, what about 3? Now you notice step 3 has a repeated matrix and no random repeated statement, but no random statement. So what's code 3 doing? What kind of a model? Marginal model? Random effects model. It's a marginal model because there's no random statement. So what kind of a marginal model is it? Compound symmetric, how do you know? Because you see, type equal to CS. So if you did this, model A, and you did model B, what do you think would happen? See, this is a random effects model, which assumes that the R matrix is sigma square I and has random intercept. This is a marginal model that assumes there's no random effect and that the R matrix is compound symmetric. If you run these two models, you're going to get the same answer for the effects of the betas. That's what you're going to get, because we've already talked about this 100 times already. And one way for you to prove to yourself that's the case is do it. You know, I've given you a bunch of homework problems, but you can always do it, you know, separately or in the context of some of these questions. So that's the important thing. Now, there's another example. I'm not going to talk about it next time. I'm not going to talk about it this time because I got other things to talk about. And this is a more complicated example that I'm just going to introduce it because in this example, in addition, this is a different posture measurement. It's called gaze angle, not shoulder flexion. You can measure posture in a number of different ways. I don't know what gaze angle is. You know, I don't know what it is. I'm just trying to be stupid here. Gaze angle, okay. So in this case, again, you've got 19 subjects. Subject one, well, I don't see it over here, but there's 19 subjects. And each of them has been measured for gaze angle on Monday, Wednesday, and Friday, AM and PM, okay? But in addition to that, there are 2 different people that are measuring them. They're measuring their gaze angle. So there are 2 raters, rater 1 and rater 2, okay? So we got days, times, raters, and subjects. So now it's a little bit more complicated, okay? Because I got another thing I've added, okay? Now, question is there an effect of day, time, and or rata and possible 2- or 3-way interactions on same question, okay? but now I got a 3-factor crossover design. Okay? It's the same question. But it's more complicated. Why is it more complicated? It has to do with this rater variable. Okay? Now think about this. Now this is actually what they had in this particular posture measurement study. This was a study done by one of our faculty members, Michelle Marcus. She did this a long time ago, but this was the issue that she had. Raters. They had 2 raters, as I said, 2 raters, rater 1 and rater 2. Okay. Question was, were these 2 raters the only 2 raters that they could ever use to measure this? Or were these 2 raters considered to be a sample from a larger collection of raters that they might have used, but it was a sample? They chose these 2, they could have chosen another 2. You hear my question? You only have 2, or were these 2 a sample? Well, what's the difference in those questions about the variable rater? Is rater should be considered a fixed effect or a random effect? If it's a fixed effect, then day, time, and rater are all fixed effects. And you could talk about day times rater, time times rater, in the model statement. But if rater's a random effect, you can't put rater in the model statement, right? Because if it's a random effect, it has to be in a random statement. You got what I'm saying? So it's more complicated. And that's part of the homework assignment that you have for next time. But I'm going to go over that next week, how you deal with that, how you do that. So that's an introduction to that. Okay? And it's sort of another more, there's all these things that gets more complicated. And I'm trying to give you complications that are at least something you can get your hands on. And when you try to get your hands on this, you find that, gee, when I try to do this, some things don't run. And I try to say, okay, well, if they don't run, can I get something that runs? And when I get something that runs, well, it's not what I would have wanted to do, but does it do something? And we'll talk about that, And I've got, see, now the difference between this example, see, in this example, and this is a third reason for using random effects, where one or more of your exposure variables, remember the exposure variable was day and time when you did shoulder flexion? Now you got 3 exposure variables. You got day, time, and rater. Rater is an exposure variable. It's not a confounder. It's an exposure variable. But if one of these variables is considered to be a random factor, then things get more complicated on how to do that. So, there's this course, and there's a program that does this, but you got to think about how you're going to do it. Okay, so, now I've got all these program statements on how to do it, and boy, there's a lot there. So let's skip this and get to this. Hypothesis testing for a random effect. Okay, so this is what this is about. What I'm now going to talk to you about is how do you test hypotheses about random effects? And I've already told you one way to do it. What's the way I told you? The Wald test, where you do this Cove testing and you get this information and you get these Z statistics and you do. That's one way to do it, and it's not the best way. But it's a way that you can do it. It's the easiest way to do it. So some people say, well, as a start, I'll do that, and I'll see whether things make any difference. Okay. So there's 3 methods. There's method 1, called an approximate LR test. LR stands for likelihood ratio. Method 2 is the approximate Wald test. Method 2 is what I sort of showed you. And then there's something else called method 3, which is called the mixture test. And that's the test that's considered to be the best way to do this. It's a little bit more complicated. But there is a computer program to do it. And it's in your course documents folder. It's in your lecture notes. It's in one place or the other. So if you want to do a test for random effects, you can use the mixture test using this program. As long as you figure out how to use it, and I'm not going to talk about how to use it today because I don't have time, but I'm going to talk about I think I'll show you how to use it or show you how it works. It's not that hard, but anyhow. So those are the 3 things. Now let's talk about each one of these. Let's talk about the second one because that's what we've already done. I've already shown you the second one. SAS MIXED and GLIM mixed provide estimates, standard errors, z-statistics, and two-tailed p-values for each variance component and the error variance in one model. in one's model. The p-value for this test must be halved to get the correct appropriate p-value. The null and alternative hypothesis being tested is that a variance, if you're talking about a particular random effect, whether it's a random intercept, a random slope, or some other random slope, any one of the random slopes, what you're testing is whether the variance corresponding to that random slope is equal to 0 or whether it's different from 0. But you notice I said greater than 0. Why didn't I say not equal to 0? Why did I say greater than 0? Can't have a negative variance. Very good. Okay. Can't have a negative variance. So you're testing whether the variance is equal to 0 or greater than 0. Why the variance? Okay, think about this. You remember the assumption that's usually made about a random intercept? What's the assumption usually made? That it's normally distributed with a mean of 0 and a certain variance. You remember that? That's what's usually made about any random effect, but for the random intercept, that it's normally distributed with a mean 0 and a certain variance. Okay? So if the random intercept is not significant, what's another way of saying, or if there's no meaningful random intercept, what can you say about that variance? Normal 0 variance. Variance has to be 0. If the variance is different from 0, then you're saying, well, then there is some effect. There is some, may not be much, but there is, you can find significance about it, but that's what you, so when you're testing something about a random effect, you're testing whether the variance corresponding to that random effect is 0 or not. That's what you're testing, okay? But you are testing whether it's 0 versus different, greater than 0, because it can't be less than 0. Now that means that if you do a Wald test, now the Wald test basically is simple. You take an estimate of this variance and divide by the estimated standard error. And that's what was done in that slide way back when over here. You took the estimate, you see the 0.2185, and divided by its standard, let's see, divided by its standard, oh no, that's not the estimate. 4.0263 divided by 3.6859 is 1.09. That's the estimate divided by its standard error, and you get its p-value. That's what you do, okay? 0.2747. That's what it turns out to be, okay? Well, that's the area under the curve, the normal curve, okay? But you notice what it says here. Now I'm going back to this thing. Yikes. Going back. You have to take the, how do you, if you have to have the p-value for this test must be halved to get the correct but approximate p-value. So what does that mean? You get a z statistic. The computer gives you a p-value, but always it's two-tailed. So what do you have to do to get half the p? You divide it by 2 to get the. That's what you do. To do this method 2. That's method 2. Easy as pie, but not the best thing. But not the worst thing, but worse than the other two. Okay. Method 1, an approximate LR test. Now method 1 is an easy thing to understand too. Approximate LR test. It's an LR test that compares two models, with and without the random effect, using a chi-square statistic, not an F statistic, with p degrees of freedom, where p is the number of variances and covariances in the G matrix that must, this is where it's a little bit weird, that must be equal to 0 under the null hypothesis that the variance components of the random effects being tested are 0. The p-value for this test must be halved. Now let's look at an example of this. Let's get to an example of 1, method 1. Okay, here's a model. I skipped a couple of slides. Here's a model. Is this a random effect? Does it have a random effect in this model? Yeah, it has a random intercept, right? Okay. So now what I want to do is I want to test to see if this random intercept is significant. So what is my null hypothesis? Well, B0I is a random variable, and I'm assuming that it's normally distributed with mean of 0 and a variance of sigma naught square. That's what I'm assuming. So I want to test whether sigma naught square is equal to 0. And I mean, because sigma naught square is the variance of this. That's what I'm assuming about this thing. I want to test it. If sigma naught square is equal to 0, then I'm saying this random effect is not significant. That's how you test for it. Okay? Okay. Now, how do you do it using this approximate LR test? Well, what do you do to do an LR test? You fit two models, full and reduced. What's the full model? This one. What's the reduced model? Doesn't have the random effect in it, right? You get the LR statistic. Now, it is maximum likelihood, so you can get an LR statistic, likelihood ratio test. Even though you assume normality, you can get an F test, but you can get a likelihood ratio. You get this likelihood. It's chi-square with how many degrees of freedom? 1, right? That's what it is. Now here's the issue here. The degrees of freedom for this test, according to what I previously said, must be the number of 0 variances and covariances under this null hypothesis that are set equal to 0. Now, what's the null hypothesis? This. How many variances are involved? Just one, right? Just the sigma naught square. So how many variances and covariances are being set equal to 0? 1, uno. So the degrees of freedom for this test is 1. That's why it's 1. That's why it's 1. Okay? Because you're only testing for, you only have a single random intercept. But I'll give you another second example where it's not clear, or you have to think about it differently. Okay? Here's another example. Okay? What's the difference between what I've now done on this slide? Okay? Okay? Look at these two models. One model has what? Random intercept and a random slope, right? This other model just has a random intercept, right? So suppose my goal is to test to see if the random slope is significant. Random slope, okay? Then what I want to do is the slope variable, the variable is B1I. And I'm assuming that B0I and B1I are normally distributed with certain means and certain variances, but not necessarily the same variance, and that maybe they're independent, maybe they're not. In fact, allowing for them not to be independent gives you this G, you see this G matrix? Look at this G matrix I have. You notice, what's sigma naught square? What's that stand for? The variance of B0I. What's sigma 1 square stand for? The variance of B1I. What's this? Sigma 0, 1, which is the same thing, both sides. What's that? The covariance between this variable and this variable, allowing for the fact that it might not be 0. Okay. Now, let's talk about how you would do this test. Okay. The full model is this. The reduced model doesn't have the random slope in it, right? That's if you want to just test that, okay, just simply. And so the likelihood ratio test subtracts the -2 log LR, reduced model, minus -2 LR for the full model, and it's a chi-square statistic, okay? Now, under the null hypothesis, if you were just thinking about the way you usually do this test, what would be the degrees of freedom for the test? 1 or 2. You notice I said 2 here, but why did I say 2? Why didn't I say 1? Well, why would I say 1? To go from this model to this model, how many variables am I dropping? 1. So that's why I might say 1. But now if I ask the question, the G matrix is a 2 by 2 matrix involving 2 parameters, sigma 1 square, sigma naught square, both of which are equal 0 on the. So the degrees of freedom is 2. It's the number of 0 variances and covariances under the null hypothesis. If the null hypothesis was true, that sigma 1 square was 0, then the correlation between 1 and 0 is also 0. This was 0. This has to be 0. So there are 2 parameters that have to be set equal to 0. That's why the degrees of freedom is 2. Got that? I mean, that's the second thing. And it's a reasonable test. It's not as good as the third thing, which I'm building up for, the great finale. right? I don't know if it's grade finale. So that's the first thing. That's method one. We've looked at method two. Now let's look at method, okay, now let's look at, did I do the mixture test earlier? Okay, method three, the mixture test. Okay, I'm skipping back here. Let's see, method three. This test, and this is what's weird, is a mixture of two chi-square statistics, a mixture of two variables. I don't think in any course that any of you have had, you've learned about a variable that's a mixture of two variables. What on earth does that mean? And if you're taking theoretical statistics, there is something. You can have a chi-square statistic and a t statistic, and there are two variables. One is distributed chi-square, the other is distributed t, and you sum them up and you say, what's the distribution of the sum of these two variables? It's a mixture. It's a mixture of two different distributions. It's weird. It's definitely weird, okay? So this is the kind of thing that puts you to sleep here. If only one effect is tested, this p-value equals a half p-value. Otherwise, it's not equal to the approximate LR p-value. Anyhow, and there's a former student, PhD student, Barbara Bardenheimer, works at CDC. He's written a macro to carry out this mixture test, and there's an example of this macro on Blackboard, and I'll try to show it next time, but not this time. Okay, so let's go to that. Okay, here's an example. Now, here's what we're going to do. Okay, we consider a linear model for the shoulder flexion data involving the single predictor time. So remember, the shoulder flexion data had day and time. I'm just saying, suppose we just focus on time. So here's the model, and the model has a random intercept and a random slope for time. Okay, that's the model we're talking about. Okay, and what we want to do is test for the significance of the random slope. We want to test for the significance of this term, or its variance, because we're assuming that this term has variance. What did I call it? Sigma t star. BI1 is normal 0 sigma t star. I don't know why I didn't say 1, but I said sigma t star. Okay, and it's assumed the R matrix is sigma square I, but sigma E square I. And the G matrix is just like we previously looked at, but now I'm talking about sigma 0 and sigma t instead of sigma, just to make this a little different. I don't know, make it more confusing. But as with model 1, there are two parameters. Sigma 1t, sigma t squared, and sigma 0t that must be set equal to 0 under the null hypothesis in order to get the reduced model. The reduced model doesn't have this term in there, okay? So method one is to compute the LR statistic that compares the above full model with the following reduced model, okay? Now, it's a slightly different example, so that's why I'm calling it sigma t squared. So here's the full model, here's the reduced model. I fit this model, I get the likelihood ratio for this model, that's LF. I get -2 log likelihood for this model, that's LR. I subtract the 2, and I have a likelihood ratio statistic. But I'm not done. I'm not done. I've got a likelihood ratio statistic. What do I do with it? The mixture test says this is what I do with it. This is the thing that blows your mind. May blow your mind. But the program makes it easy. And actually what I've illustrated makes it easy. The mixture test then assumes that this likelihood ratio is approximately has the following mixture distribution. 0.5 times a chi-square with 2 degrees of freedom plus 0.5 times a chi-square with 1 degree of freedom. What on earth is that? Okay? Isn't that what you're saying? What is that? Okay? Now, what we're talking about, you have a variable that you're assuming is chi-square with 2 degrees of freedom, and you have another variable that's assumed chi-square with 1 degree of freedom. Why 2 and 1? Why with the 2 and the 1 in there? First place. Because it had to do with what happened when we did try to do that approximate Wald test. Approximate Wald test sort of said, well, maybe the degrees of freedom should be 1, because going from this model to this model, you're only dropping 1 variable. But maybe it should be 2, because if you think of the number of the number of parameters that have to be set equal to 0, maybe it should be 2. So you've got a sort of a question, should it be 1 or should it be 2? That's why it's, and so this is the formula for it. Chi-square 2, chi-square 1, okay? Now, essentially, that's what I say. This mixture reflects the viewpoint that the appropriate DF should be the sum average of 2 degrees of freedom corresponding to 2 parameters that need to be set equal to 0, and 1 degree of freedom corresponding to the 1 parameter that is the primary parameter of interest. That's all I just said. Okay, that's why that's there. Now, this is how it's computed, but it can be computed using the program by just telling the program what the two models are, and the program will do it for you. But look at this. See, this is a formula. This is a formula. Okay? It says P stands for p-value, 0.5 times a probability of a chi-square with 2 degrees of freedom greater than LR. What's LR? LR is that thing you computed here. That's the likelihood ratio you computed by comparing these two models. So you get this LR by comparing these two models. That's how you get that number LR. Okay? And then you look up under a chi-square with 2 degrees of freedom what the probability of a 2 degrees of freedom is greater than that LR. And you do the same for chi-square with 1 degree of freedom greater than LR. You look up these two probabilities, and then you put it into this formula, and you get a p-value. Now, for example, if LR was 4.6, if LR turns out, if the likelihood ratio test that you got when you actually did this was 4.6, you'd be going 0.5 times this probability plus 0.5 times this probability. And it turns out when you go to chi-square with 2 degrees of freedom, you find that this probability is 0.1. When you go to chi-square with 1 degree of freedom, you find that this probability is 0.03. And you just do the algebra and you get 0.07. That's the p-value. That's how you do it. That's the mixture test. Now, why this is better than either of the other two? Theoretically, somehow it's better because it's dealing with this issue about these two ways of doing it and what the G matrix is and all of that stuff. That's sort of why it's better, according to these two guys, two Belgians. Where are they? I don't know where they are. They're somewhere. Two Belgians wrote this thing, wrote the thing. And they wrote this book, and that's how you do it. That's the better test. So that's what you do. If you want to test for a significant random effect, the mixture test is better, and there's a program to do it. Okay? So we sort of have it here in terms of all the things I wanted to do today, except there's one other thing I didn't do today, and I'm just going to introduce, and then I'm going to let you guys do it. I'm going to still give you 10 minutes, but I want to introduce one other thing, because there's a whole nother example that has to do with the FEV data set that I want to introduce, but we're eventually going to talk about it at another time, although I want to introduce it now. Here. I don't know whether you're going to love this or not. You probably hate it because you want to get out of here, maybe. But anyhow. No, because you love this course. No. I'm talking to myself. Okay, so this is a second FEV example. Okay. Now remember what the FEV example was. There was a certain place where there were 40 kids, and they had 5 weeks of observations of their FEV scores. Okay, and you wanted to see whether the FEV changed over the 5 weeks. Okay, now here's the issue. Second example, there are 2 locations, not one location. In the previous FEV thing, we only had one place. There were 40 kids, and they were exposed. But now I'm talking about there's 2 locations in the same city. 40 children in each location were examined under normal conditions, then during an air pollution alert, and on 3 successive weeks following the alert. Location 1 was located within the neighborhood of the source of the pollution, whereas location 0 was located 10 miles away from the source. See the problem that's different now? Previously, we just had this one location. It was either right where the pollution occurred or it was 10 miles away. It was one of these 2. Let's assume that location 0 is it's one of these 2, 10 miles away. The primary study objective was to determine whether the change in FEV1 over the 5 weeks differed in the two locations? It's a different question. Whether the change in lung, and the way this, it says the primary study objective, so this is not even a random effects question. Did the change in lung capacity, FEV1, change over the 5 weeks? Well, that could be asking in a number of ways. One way it could be saying was you got two locations. You got 5 average scores at one location. You have 5 average scores at another location. Okay, and so what you're saying, what you're asking is, and then you have an overall average for each location. The two locations overall average different? That's what you're sort of asking. That's one way to say it. Another way to say it, whether week 1 versus the other 4 weeks for location 0 differs from week 1 minus the other 4 weeks for location 1. That's another way to do it. So that's a second question. You see that? You see how it's more complicated? Because now I have 2. And this, you might say, this is just a little extra example from the FEV, but what does it do to us? Well, here's the data. Here's the data. Now, instead of 40 kids, I got 80 kids, right? I got 40 kids from one location. I got another 40 kids from location 0. You follow me on this thing? This isn't hard to talk about. Okay. Now, I'm not going to talk about it too much, but okay. Now, let's look at the model, the scalar version of the model. Let's not even worry about the matrix version of the model. Okay. Look at this model. Look at this model. Scalar version of the model. Can you get a handle on what's in this model? First of all, you notice it says it's an expected value for me, so there's no error term. But you notice it's beta 0, beta 1, beta 2, beta 3, and beta 4. T1, T2, T3, T4. You see this part of the model? That's just like it was before, right? Just like it was before. Okay. Now what have I done? I've added a variable called G. G says, are you in location 0 or location 1? It's a dummy variable. 1 if location 1, 0 if location 2. Okay? That's what G is. Now what's this? GT1, GT2, GT3, GT4. These are interactions of G with time. Okay? That's the model that I'm starting off with. The simplest model, a simple model that I'm starting off with to answer this question. Okay? Now let's just do a little bit with it, and then I'm going to stop because I want to give you something, sometime. Okay? Now, look at this model, and for example, if you look at this model, and for example, think about this. If G is 1, if location 1, 0 if location 2. Suppose you're in location 0 if location 2, right? I don't mean that. It's location 0. Should have been location 0. So suppose you're in location 0 at week 5. This is meant to be location 0. Okay. Suppose you're in location 0 and at week 5, and the reference group is week 5. Okay. What happens to this model? Reference group is week 5. What's T1, T2, T3, and T4? 0. What's G? What's GT1, GT2, GT3, GT4? 0, right? So if you're in location 0 at week 5, the model reduces to beta 0, right? Right? So that's what I'm saying. Look, so now, but now, what if you just say, there are other things. So what about the other parameters? What about, so beta 0 is what happens if you're in, so beta 0 is mu 5, 0. It's the mean for the 5th week for location 0. Okay, that's what beta 0 is. What's beta 1? What's beta 1? Well, it turns out that you can solve for this. I'm not going to get into all this. So you can solve for all this. Turns out beta 1 is mu 1, 0 minus mu 5. You can actually solve for each of the betas in terms of the mu's. What you can solve for. Now, again, I'm going to talk about this next time. But let me ask you this question. What if there's no interaction? No interaction. How would you state that? See what I've written down here, bottom of the screen? Beta 6 equals beta 7, beta 8, beta 9 equals 0. Does that make sense? If beta 6, if all those product terms, coefficients are all 0, there's no interaction, right? So what would the, see this picture? Is that no interaction? Right? That's no interaction. So if you wanted to test for that, that would be the chunk test for it. So there are things you can do with this model that I've done with this model using, I've got the data, I've made up the data. Now it turns out that if you look at the data and you actually plot the data, this is what you actually get. And you actually plot the data. Then I'll stop at this point. But look at this. What does it look like? Does it look like there's interaction or no interaction? Look like there's interaction because you don't get that. You don't get that picture. You don't get that picture. You get this picture. Now, statistically significant, you have to find out whether it's statistically significant or not. But there's a whole bunch of things you could do with this, and this is another example that goes, gets more complicated, where you're now comparing two groups, and you've got correlated data in each of the two groups. And you may have a problem like that. Your project may involve two groups, and you may have correlated data. So I'm going to stop with that. That's where I'm ending today. Okay, but that's the second example, and I'm going to show you either next time, I'm going to show you what happens when I run this thing. What and you test with it. What do you get? Okay, so that's the second example. So I'm done there. Okay, so now I'm going to stop the recording. Okay, is that all right? Stop.